Hello everyone, here is Math 6380P final project presentation for the next period image classification by Caoyang and me. In this final project, we use the scattering net to do feature extraction and would later compare the results between extracted features and the raw data. We first visualized the features as well as the raw data to get some brief idea of their differences. The methods we used to do the visualization contains PCA, MDS, and t-SNE. And after that, we use traditional methods to do classification on both the extracted features and the raw data to compare their performance. And the data set in this project would be next period image classification. And here, let me first introduce the data set. So this next period image dataset is made up with image of semiconductor devices with two main classes, the good ones and the bad ones, also called the defect ones. So for example, in this picture, the first one is the good one and the last one is the defect ones. And our goal is to do some binary classification to separate the two classes. And the dataset contains 34,457 training samples and the 3,830 test samples with the same good and the defect ratios. That means in both the training set and the test set, the good and the bad ratio are the same. And each sample in this data set is just some image of shape 3 channels, and one thing I want to mention here is that the width and the height are different for 267 times 275. And the method of feature extraction we used here is the scattering net. It is quite similar to the convolution neural network, and the difference is that it contains no training before the classifier. It used wavelet filters directly, and it outputs are from each layer. So the black dots are the outputs from each layer. It provides some sparse and sparse matrices. That means it gives more stability. It contains some deformation stability in the invariant data translation. So for example, in the data set of the handwritten images, digits, the same digits lies on the same planes. For example, 3 and 4, the 3 lies on the blue plane and the 4 lies on the orange planes, and the different shapes just means the different positions on the same plane. We use the Kymatial Lab package to do the scattering net. And then for the image classification methods, we use four traditional classification methods. So the first one is the linear discriminant analysis, LDA. So it assumes samples in each class follow some normal distribution, and also the covariance metrics are the same. Our goal is to maximize the likelihood and find the linear space to maximize the separability between groups. We want to produce some new access to project all the samples to maximize the difference of two means and minimize the variation. It can be very sensitive to outliers. Next method we used is the support vector machine, SVM. We want to find some hyperplane so that the soft margin, also called the support vector, are the maximum margin classifier. And that means, for example, in this one, we used a red hyperplane H3 that will be the best hyperplane to do the separation, to do the classification. Next method we used is the random forest. It constructs a multitude of decision trees, and we random select some subset of the data set, and that process is called the bootstrap. After that, we did the output of the result for some kind of average results in some individual trees, and that is called aggregation. So as we use bootstrap and then aggregation, it somehow avoids some overfitting and may reduce the variance. Last method we used is the logistic regression. It is also used in always used in some binary classifications. It is very easy to train and very efficient, and it has some S shape, just a logistic regression. And for logistic regression, we want to maximize the likelihood, and for the linear regression, we want to use the least square mean method. And for visualization, the first method we use is PCA. PCA want to preserve the variance of the data as much as possible. So as we can see from on the left hand side, this one is the PCA on our extracted features on the scattering net, and the right hand side is some raw data on some raw data. And on the raw data, it's just randomly distributed. And on the scattering net, although it cannot give a great separation or great classification, it can somehow converge to some point, and then the multi-dimensional scaling (MDS). It want to project the top left singular vectors from the data, and it preserves the distance as much as possible. Again, we can see here from the left hand side it is on the features, and on the right hand side it is on the raw data, and also on the raw data it is totally randomly distributed. And for t-SNE, it seems that we can find it converts to some circle structure instead of some angular structure. And from the result, the test error and the training error part, we can find that although directly doing classification with the traditional methods has lower training error, it may have higher test error. That means it may get some overfitting. So scattering net somehow can help us to avoid overfitting. And also for similar to the project 1, we did the statistics. For NC1, has some dimension explosion. For the as the Python cannot do the SweDo inverse directly. We have to do it manually. And for the remaining parts, it seems not so close to 0. So although the features extracted by scattering net may not satisfy the neural collapse assumption, the features would be more organized and would converge to some other simple structures, for example, a circle like that. To conclude that this result is not so good, so maybe we need other methods to do more classification methods. And that's all. Thank you for listening.